Hello, here's our next linear algebra video about examples of some solution sets. So remember, the solution set of a system, like one of these three systems here, is the set of all xy ordered pairs that makes each of the two equations true. And if you want to solve a system, that means find the set, describe the solution set that satisfies each of the two equations in each one. And one way to do that is to graph the lines. If they are linear equations, that's not too hard to do. So once you graph a line, what you're really graphing is a picture of all of the xy pairs that make any one of these equations true. In a moment, I'm actually going to ask you to pause the video to work on this problem yourself, whether it's an exercise or example, whatever EX is short for. You should be able to at least graph all of these lines. If you're not sure exactly what format I want to see the answer in, don't worry about it. You can fix your answer when I show them after you're done. And by the way, pausing videos to work on problems yourself or to write things down yourself or just to ponder about things is always a good thing to do. So not just when I say pause here like I'm about to do. You'll always learn more from a problem if you do it yourself rather than seeing somebody else do it. And even if you don't know how to approach a problem, just pausing the video to think about it for a minute will make the solution more meaningful when you see it. And when I actually say pause here to do an example like I'm about to do right now, that means it's a mandatory part of this homework assignment for you to really do it yourself. So with that said, the answers will show up in about 10 seconds. So pause here. So here are my answers. So you might have graphed it in different ways. For the first equation here, x plus y equals 5, I just thought of what are two ways you could make these two numbers add up to 5, and what if one is 0 and the other one's 5? So that gives you the actual x and y intercepts, and then you can just draw the line through those points. You could also use slope-intercept form here to just start plugging in 0 and then adding 1 to x each time to get some other y coordinates, and that gives you the points on this green line here. And the only point that is actually a solution of both of the equations is 2, 3. So I'm writing it in braces like this to just say I'm talking about a set of objects. Even though it's really just one thing, it is a fancy way to just say, to make it clear that you're talking about a set, not just one point, even though it really is one point. Okay, so with this next one, you can see that x plus y equals 5 cannot be true at the same time as x plus y equals 3. Whatever x plus y is, it can't be 5 and 3 at the same time. And you can see that there's no point of intersection of the solution sets of the individual equations. So that means there's no solution. So you can say the solution set is empty. And there's actually a fancy name for this that we're going to define right here. An inconsistent system has no solution. Inconsistent here basically means we're talking about two things that can't be true at the same time. Just like if somebody was being investigated for a murder or something, and they said, "Oh, what time did you leave work?" And the guy says, "I left work at 2:45." And then they say, "What time? What did you do when you get home?" And they say, "Oh, I turned on the TV and watched Judge Judy." And they say, "Oh, how long does it take you to get home?" "Oh, it takes 15 minutes." And then if the detective knows that Judge Judy actually starts at 5 p.m., then how could it be that they say they left work and they should have gotten home at 3 p.m., but then the first thing they did is they turned on a TV show at 5 p.m. So where were they between 3 and 5? That's an inconsistent story. Same thing here. So, all right, so with C, you might have realized that these two equations are just different ways of basically writing the same equation. I mean, they're not exactly the same equation because, for example, one of them has a 6 in it and the other one does not have a 6 in it. So they're not exactly the same equation, but they are equivalent in the sense that you could turn one into the other one by just doing the same thing to both sides of that equation. And in other words, they also describe the same set of points, which means, in other words, their solution sets are the same. So here's the solution set of one of them is like it contains the points 0, 6, 1, 4, and 2, 2. So it's all those points on that line. And here the solution set of the other one contains the same points. So the solution set of the system is just all of those points. So there's an infinite number of solutions. Now there's actually another way to write this. You could write this in what's called set builder notation, or you could also call this parametric form. And the way to read set builder notation, the set builder means that there's the braces, and then this line in the middle, and the line there, think of that as meaning such that, and the braces mean like the set of all of these objects such that this other thing is true. So this is another way of saying the set of all points of this form where the x coordinate is just x and the y coordinate is equal to 6 minus 2x. So the set of all coordinates of that form where x is any real number is another way to read this. So that's a fancy kind of better way to answer the question. It's more specific than saying there's just an infinite number of solutions. But when you just say there's an infinite number of solutions, what are they? Well, this one here is another way of describing what they are. That's kind of basically saying the same thing as just one of the original equations themselves. So, but that's an important way we're going to have to write things later on. And I defined what an inconsistent system was. Almost forgot to define what a consistent system was. You could probably guess a consistent system is one that has at least one solution. So you can see here it either means you have one solution if you have two lines that intersect at one point, or it means there's an infinite number of solutions. At least if we're talking about equations with two variables where the graphs are on the xy plane, you can probably see that linear systems with two variables, x and y like we have here, have 0 solutions or one solution or an infinite number of solutions. Those are the only way you can arrange, the only three ways you can arrange two straight lines. They either do not intersect because they're parallel, or if they, or maybe they intersect everywhere because they're parallel, or they just intersect at one point like this. And you might be thinking, wait, I have a way I can make 3 different lines intersect at 3 points, like this one, and this one here. But actually none of these points are actually solutions of the system of 3 equations, because this point here, for example, makes these 2 equations true, but it's not actually a point on this line over here. So that point's not actually a solution of the system of 3 equations that we have here. So there's only those ways you can do it: 0 solutions, 1 solution, or an infinite number of solutions. And it turns out this is true with more variables too. Even if you have systems with 3 variables or 4 variables or 100 variables, the number of solutions you have is always going to be 0, 1, or infinity. But we'll have to see why that's true later on. And I just realized I drew like a weird fox or something.